Hi, everyone. Thanks for having me. Excited to be here. I thought I would talk about just kind of a broad blockchain intro, since this is an audience of front-end developers. When I started working at Kadena in blockchain a little over 5 years ago, things were a lot less developed, and I kind of had to learn a lot of this stuff on my own along the way. And I think I can kind of distill things into a way that hopefully will give people a decent sense for what's going on, and then provide a building block that you can use to create your own applications. So it's going to be kind of a whirlwind, just intro to blockchain and some of the concepts. But I'm really assuming just some basic front-end knowledge, some basic programming knowledge, and hopefully we can make things understandable. So moving on, just a brief outline. First, I want to talk about currencies, because that's kind of where this all started with Bitcoin. Then I'll talk about blockchains in general, and proof of work, a little bit more about smart contracts and dApps, and then about some details of how Kadena scales, and how building on Kadena is the best way to make sure that your applications will have low reasonable fees for the foreseeable future. So, currencies. What is a currency? I think one of the biggest innovations here that Satoshi made with Bitcoin was really realizing that an accounting ledger is a currency. At the end of the day, all you need to know is who has how much, and then you can have some sensible rules for how that value can get transferred around, so that you're not, making money out of thin air and destroying money and things like that. But at the end of the day, an accounting ledger is a currency. And you see here, if Alice has 20 and Bob has 5, and then we do a transfer where Alice is transferring 10 to Carol, then all we do is we update our ledger. And now Alice has 10, Carol has 10, Bob still has 5. Now, let's just go through some examples of currencies throughout history. Physical assets, gold, cash, etc. For thousands of years, people used physical assets as their currency. And you might ask yourself, well, how's that a ledger? No one's keeping a ledger. Well, actually, physics is keeping the ledger for you. Physics is the thing that says it's really hard to create more gold out of nowhere. In the case of cash, it's maybe some physics plus some laws that says it's illegal to forge currency and make your own. So physical assets are actually still a ledger in the same sense that we're talking about. Also, a traditional bank. Somewhere they have a ledger of balances that says Joe has this much, Carol has this much. It's really the same thing. Another example, airline ledger of customers and miles. Airline miles are kind of a currency. You can spend them in much more limited ways than fiat currency, but they still behave very much like a currency all the same. Retailers with reward points, same kind of thing. A centralized entity is keeping track of this ledger of who has how much. And then I added just an extra one for a little bit of humor, but also I think it actually functions as a currency as well, as like a mob boss and their little black book of like people that owe them, or a bookie or something like that. If you kind of stretch your brain a little bit, you can really see, they're probably trading some stuff. People might say, oh, well, the mob boss can do whatever they want. Yeah, they can, but if they are too crazy with how they manage their book of debts, they will lose credibility, and then they'll probably have some kind of power struggle or something. So mob bosses are still somewhat constrained, maybe not quite as much as a traditional bank, but there's a lot of commonality here, and these are all currencies. And Bitcoin came along and realized that it's really just a ledger. So what are the requirements? There's a few things, and if you take my mob boss kind of flexible definition of currency, maybe not all of these requirements are strictly required all of the time, but some of the things that we expect out of currencies are that transfers from one account to another have to preserve the circulating amount. We usually aren't creating new currency when that happens. And we also usually have restrictions on how the circulating amount can be increased or decreased. In the case of fiat with US dollars, the Federal Reserve can print more, and we've kind of, as a society, decided that that was a good thing. Not everyone agrees, but it is what it is. And then another requirement is that the ledger can't be tampered with. And by tampered, we really mean like tampered in the ways that aren't kind of agreed upon in the system. And of course, in the case of the Federal Reserve and fiat, usually someone has printing powers. In the case of cryptocurrency and Bitcoin, sometimes these abilities to print new currency are predefined upfront, and so they won't be able to be tampered with depending on the currency. And there are some other requirements that you can probably think of, but I didn't bother to mention here. Now, all of this works because we trust the entity maintaining the ledger. In the case of physical currencies, well, we trust physics. And we also just kind of deal with the fact that anyone who can find some more gold somewhere deep underground, they just get it because, that's just the way it worked. That was the best we had. But we have to trust banks to maintain your balance correctly. Same thing with corporate reward points. And as I mentioned, we also have to have a certain amount of trust with the mob bosses because they won't be able to stay in power if they just go crazy. The thing is that because we have to trust these entities, we're beholden to them. This gives them power over the ways that these currencies are handled. They can deny accounts to certain people for whatever reason they want. They can impose inconvenient or expensive transaction requirements. They can also have unpredictable behavior. And that impacts the people who use the currencies. But if we use them, if we decide to use those airline miles or the retailer reward points, you're implicitly saying, I trust what you're doing. And of course, you can also keep track of how many points you have, and you can kind of reconcile it. And in my parents' generation and kind of early in my lifetime, that's what you did. Every month, my parents taught me, you go through your bank statement and you make sure that your balance matches what the bank says. So you're kind of checking up on them, but you still have to trust them. Now, moving on to blockchains and proof of work. The first blockchain, Bitcoin, really revolutionized things because it was the first time we could do any of this stuff digitally in a way that we didn't have to trust a centralized authority. And what Bitcoin did was they put a ledger into a special data store called a blockchain. And what we are trusting when we use Bitcoin is we are trusting Bitcoin's consensus algorithm, which is called proof of work. And if you like research it and learn about it and understand how it works, which we're going to go into a little bit here, this is really the thing you're trusting in. And you don't have to trust in the whims of a human who might change their mind and amongst other things. Or even not change their mind, but just make mistakes. So Bitcoin came along with this idea called proof of work. And the key thing is that it functions as a tamper-proof data store. So if you stick this accounting ledger into this generic data store, which a blockchain is really just kind of like a data store. I didn't use the word database just now because that kind of gives people pictures of like SQL and stuff like that. But it's a data store nonetheless. It groups data into blocks. And then you calculate the hash of everything in the block plus a random nonce. And you only accept the block when the hash is less than a small number. Some examples. If we have some data, which is just the data that's going into our block, and then we add this number 5, which is what we call the nonce, and we hash this up, we get 5E333. Well, I'm going to say that it needs to be less than 10000. This is hex. And so this is not less, so no good. But if you hash some data and the number 10, and I actually did this with a hash function in Kadena's Chainweaver wallet, which lets you run some simple code like this. This actually starts with a 0, which means it's less than 1000. So this is a good block. And I had to calculate roughly 16 hashes in order to figure this out, because each digit, if you understand hash functions, every digit has an equally likely probability of being any of the 16 hex values, and each digit is independent. If we hash some other value, 1017, actually we see a 0 in the beginning again. And again, if you see this, you'll know, oh, there's probably, they had to do a little bit of work in order to figure that out. There's a 1 in 16 chance that the hash will start with a 0, and there's a 1 in 16 times 1 in 16, i.e. 1 in 256 chance that the hash will start with 2 zeros. So when you go to the Bitcoin block explorer and you see that this block has this hash with this huge number of zeros, you can immediately tell yourself, wow, that does not happen accidentally. You have to have lots of computing power to try a whole bunch of different hashes before you find one that happens to have this many zeros at the beginning. And so you just see this. You can actually, if you don't believe this block explorer, you can download the block and you can hash it yourself. You can calculate that hash and you'll get all of those zeros. And that is what we call the proof of work. It proves to you that a lot of work was done in calculating this block. That means that people can't change what's in the block without completely screwing up the hash. All those leading zeros will be gone if the block is changed. So you have kind of this authenticity stamp that this block is the same as it was way back when it was first created. No malicious entity could have gotten control of that amount of computing power because the whole world is doing this. And it's been doing it for years now. And if you go back years, it's just astronomical the amount of power that someone would have had to be able to rewrite something in a block that's older than a certain amount. So Bitcoin is a currency because we stuck this transaction or this ledger into a blockchain, and now it can't be tampered with outside the rules that the system is programmed to allow. Money is transferred in Bitcoin by posting something on a public message board, essentially. You say, hey, transfer 5 from Alice to Bob, or actually, it should have been the other way around. I made a mistake in my slide. If this is from Alice to Bob, it should be Alice's signature signing this. And you just post that on the wall, and everyone says, oh, okay, Alice transferred this money. They check the signature. It's good. So now they update their balances. And we're using public and private key cryptography to control who can spend what money and make it so that only you can spend money that's in your wallet. And all of this stuff is stored in a blockchain data structure, and it can't be tampered with. Now, smart contracts and dApps. Ethereum came along and said, what if we, instead of putting an accounting ledger in this store, what if we put computer programs in the store? Then those computer programs can keep track of their own ledgers. And this was just an incredibly powerful idea. And we call these things smart contracts. Smart contracts make the money programmable, among other things. And these smart contracts are tamper-proof. So we can all agree, like, hey, this is what the code says. This is how it's going to behave. Occasionally, there are bugs, which means that it behaves in a way we didn't expect. But as software people, we work to get a handle on that, and Kadena has its own solutions for that we think are much better than a lot of the other stuff. And Ethereum was the first blockchain to create this. Smart contracts are really just code in a blockchain. dApps. I think the word dApp does a little bit of a disservice because it makes us think, oh, it's this crazy new thing. It really isn't. A dApp is just a normal web app that also happens to talk to a blockchain. You have the same HTML, the same web browsers, the same CSS, JavaScript, but in a dApp world, you're making API calls to blockchain resources, and you're potentially posting transactions on a blockchain or signing things with public and private keys. So Web3 is really Web2 plus some blockchain stuff. And I think that we shouldn't make it more intimidating than it should be. And then a dApp makes these API calls to smart contract code that is code stored in the blockchain. Now, current blockchains can't process very many transactions. Bitcoin handles about 5 transactions per second. Some of the others can maybe do more, 10, 15. We're talking at best 30 transactions per second for the proof of work blockchains out there today. But this is not good enough to handle the world's transaction volume. Visa and MasterCard process thousands of transactions a second. And this is called, in the industry, we call it the scaling problem. And the big user-facing effect is that it has high transaction fees. You have to compete with all of the other users to get your transaction into the 5 transactions per second or whatever the capacity is. Now, roughly speaking, all single-chain proof-of-work blockchains have the same performance, which, as we saw, is 5 to 30 transactions per second. They have the same fundamental physical limitations of speed of light, network bandwidth, transaction execution time. One chain can do 5 transactions a second. Well, we can scale this similar to how we scaled computers by having multiple CPUs. If one chain does 5, 2 chains should be able to do 10. 5 chains should be able to do 25 transactions per second, and 10 chains, 50 transactions per second, etc. This is the basis for how Kadena scales, but it has one hitch, or kind of 2 challenges. 10 separate blockchains means that you have 10 separate currencies, and that would be a pain to deal with. And a 51% attack, which we didn't really describe here, but you can read about it elsewhere, becomes a 5.1% attack. You only need to have 5.1% of the network in order to start to potentially change some recent blocks. Well, we can do something about these issues, and that is what Kadena has done. And the solution is to braid the chains together. So if we only had 2 chains, this is really how it would look. Each chain, instead of only being connected to itself, would also be connected to the other chain, kind of like it contains the hash of the previous block and the hash of the previous block on the other chain. This braiding solves the problems. It allows you to, after you wait 1 block, now you have to have the whole network hash power in order to attack one of the chains. And it also allows you to do cross-chain transfers because the hashes are included in other chains. And if you can transfer from one chain to another, now your multiple currencies behave as a single currency. So the braiding solves both the problems for us, but it's not quite enough. 2 isn't enough chains. We need to be able to go higher than that. Here's what the 2-chain graph looks like. How do you connect more chains together? If you connect it like this, there's too many lines in this graph. There's too many hashes per block. This doesn't quite work. It requires too much space. If you connected it in a different way, it's not very much space, but it takes too long to get from one chain to another to get to all the other ways, 5 hops. But math saves the day, and this is the brilliant realization that Kadena had. The degree diameter problem from graph theory solves exactly this challenge. By connecting, if we connect 10 chains together in this shape, it's only 2 hops to the farthest chain, and you're only storing 3 extra hashes per block. That gives you reasonable space requirements, and that makes this thing work. We know how to do this for many, many chains. For 20 chains, here's what it looks like. It's 3 hops to the farthest chain and 3 extra hashes per block. This is great, and this is what Kadena is using today. What about more than 20 chains? The math people have been there ahead of us, and they have solved this problem. This is a table that shows how large of graphs we can construct. And we can see here that if we go to 8 and 8, we can get to 734,000 chains. There's no way we will ever need more than that. So we will never need more than 8 hashes and 8 hops in the diameter of our network. That will handle global transaction loads. So I can hear you asking, when will this be ready? Kadena has already launched. This is working. It is out there, and you can use it today. In October 2019, we launched with 10 chains. In January of 2020, we expanded to allow full smart contracts after this little testing period. And in August of 2020, we doubled our network capacity while it was running to 20 chains. This gives us low gas fees. It's well understood in the industry that, as this tweet says from a prominent person, Vitalik, the creator of Ethereum, the only solution to high gas fees is scaling, and Kadena has a scaling solution. High gas fees are very harmful to the industry. And just kind of going quickly, there's a few areas that I wanted to highlight that show the examples of high gas problems. This Constitution DAO, users were going to donate to like buy the Constitution, and they spent so much on fees. The median donation was $200 something, and they were paying $50 to $90 in fees to donate. So it really just kind of kills you. And then the auction bid failed. So if they wanted to get their money out, they had to pay another $50 to $90 in fees. And it just really made it a bad experience for people. MEV is a way that enterprising individuals can come in and kind of look at what people are sending to the blockchain, and they can kind of jump in front and try to extract some money. This is also something that if you had low fees, you would be able to design your transactions so that if the value goes down, your transaction fails, and then you're not out a whole bunch of money. It just keeps our market small. You'll never be able to buy coffee with cryptocurrency if the fees are above $5. You won't be able to do small in-game NFT purchases because it just won't make sense. If you have to mint an NFT for several $100s, that excludes many artists, and it really hurts adoption. And I think the key to reaching a broader market is keeping these fees small, and that's what Kadena's scaling allows us to do. Layer 2 is another approach that people have taken to solve this problem, and it definitely has value. I think layer 2s are going to be a very important component in the blockchain story, but they don't completely solve the problem because they often end up being app specific. They don't necessarily, you have to pay your high fees in order to like go back to the main chain and interact with other dApps. You may sacrifice decentralization. So it definitely has its place, but it's not a substitute for actual scalable base layer. So in conclusion, Kadena has a scalable layer 1 proof of work blockchain. It is running today. We launched it in 2019, and it can keep gas fees low. If the gas fees get high, we can add chains to add more capacity. Now I will open it up for questions. If anyone has some questions to ask.
I definitely have questions. So many questions. And I would say, first off, Doug, how do you say it? Because like I've heard Kadena, and I know that I work at a company called Ivan, and people are like Avian, or like say it so many different ways, or Kafka, you know, like so many. So how are people supposed to say the company?
So we had this conversation internally years ago, and the decision that I remember was that the word Kadena is based on the Spanish word for chain, which starts with a C instead of a K. Cadena. And so my recollection is that we decided to say the Spanish pronunciation is the one that we are going to go with, which would be Kadena. But I think you'll hear lots of Kadena people saying various pronunciations. I don't think everyone is necessarily super strict about it, but yeah, Kadena is the way that I tried to say it.
Okay, cool. Because I'm like, I am so like mixing it up so many times, but I'm like, there's a lot of terms like that out there. the names are so easy. Okay, so the big questions coming up. What's the number one reason you would recommend pairing with now I'm good Kadena? I'm gonna look Kadena with Vue.js.
I think I'm gonna have to go with what I had in the slides.
Cool.
It's really the scaling, because that's the thing that we have solved that no one else has what I consider an adequate equivalent to. And it might not be a huge factor today. It is a factor in some cases because there are blockchains that have high fees, but there are some other blockchains that don't. But Kadena is going to be able to keep those fees reasonable when hundreds of thousands more people are using it. And that, I think, is the really compelling value proposition. The apps that you build now, they will be able to stay reasonable fees far into the future.
Very cool. Thank you. And I'm pretty sure you covered this one as well with the blockchain increase when more chains are added. Does the block time increase when more chains are added? I believe you talked about that as well, especially because you were talking about how with what going up in each measure, how many can go at the same time.
Right. I actually think I didn't mention block time specifically,
okay.
but no. The block time does not increase when more chains are added. We started out with 10 chains, and our block time is the same today, 30 seconds, as it was when we had 10 chains. Block time does not change at all. This is just like Bitcoin. The difficulty of the network automatically adjusts to keep the block time the same. With Bitcoin, the block time is 10 minutes. And if more computing power comes on, then it adjusts so that blocks still appear approximately once every 10 minutes. And Kadena works the same way. Kadena's block time has nothing to do with the number of chains, and it will stay the same no matter how many chains we add.
Very cool. And what makes Kadena different than Ethereum?
Great question. So, this could be a whole nother talk in and of itself, but I'll hit some of the highlights. So Ethereum used to be proof of work. They famously switched to a different approach called proof of stake in the last couple of years. It was like a long, ongoing, gradual process. So one main difference that I would say now is that Kadena is proof of work and Ethereum is proof of stake. I know why Ethereum switched. They did that because they thought that was the best way to help them scale. But it's actually not. It's actually harder to scale proof of stake. But if I was Ethereum and if I hadn't thought of the way of scaling proof of work, I probably would have tried that as well. So now Ethereum is not using proof of work. And I think that is a risk. Proof of work is the thing that's really tried and tested. Proof of stake, much less so. So I think that's a risk for anyone building applications. So that's kind of one big obvious one. But we have also developed a smart contract language called Pact that I think is a lot safer. We have a website, savedby.kadena.network, that kind of outlines a lot of the hacks that have happened and bugs that have caused tons of money, like hundreds of millions of dollars to be lost. A lot of them on Ethereum, but also in other projects. And in many of these cases, we've analyzed what happened at the software level. And if you just used Kadena, you couldn't have even had those bugs. In not all of them, some of them, okay, you would have had to take some better practices to stop them, even with Pact. But for a lot of cases, the bug just can't happen. And that's something that makes it different. With Kadena, you have much better visibility into what transactions are doing on the network, because the on-chain code is human readable, and in Ethereum it's not. It's a EVM bytecode that's not human readable, and so I think this makes it a lot easier for people to learn about Kadena, because you can actually look on chain and you can see the actual code that was used, and I think it makes it safer and easier to explore and audit and things like that. Those are just kind of three of the highlights.
I like it. Thank you. And so one thing, there are costs that come up, and how to predict the cost, because I love the fact that we can actually see it and conceptualize it. But how do we predict costs and cheaper and like the behind the scenes and what people are like, I can learn the tech, but I need to know how much it's going to cost me.
Right. So costs on a blockchain, they're very difficult to predict because they're driven by demand. If there's 1,000 people trying to get transactions in, and if there's only 5 slots, in this particular second, then people are going to have to bid up and they're going to have to pay more money for their transaction. And so it's predicting costs really becomes a question of predicting how many people are going to use this thing. And that's really difficult to predict. But will Kadena's costs always be low? No, there will be periods when a lot of people want to transact on a particular chain or maybe on all of the chains. And it will go up for a while. But the key thing about Kadena is we can add more chains to create more capacity when we see that that's needed. So you won't be doomed to have these higher costs. In the early days of Ethereum, an application called CryptoKitties was created. It got really popular and the transaction costs went through the roof because everyone was wanting to do CryptoKitties transactions and they couldn't get more transactions into the network. Could you predict that? Could anyone have predicted the boom of this weird app for trading cats? Nah, I couldn't have predicted that. So there's just a certain amount of unpredictability, but the predictability that Kadena brings to the game is that we will be able to add capacity when it's warranted.
Very cool. Very cool. And I know we got to go to the next question, but I'm like, now I want to go look into that because I'm like, trading kitties. Okay. But like when we're wondering like about how safe blockchain is with a quantum computer, is that something that we need to be concerned about? Because it seems like quantum computers can crack hard hashes in a very, very short time.
This is a great point. We get asked it a lot. There's really 2 fundamental choices that are the really important things to think about. One is the hash algorithm, because as I described, that hash algorithm is crucial to the proof of work. And then the other is the public-private key algorithm that we use to decide how ownership of accounts is handled. And we need to ask, for these 2 things, how are they hold up to quantum computers? So Kadena's hash function is called B.S.c. It's a pretty modern hash function. It's very well understood, and we chose B.S.c because it is quantum resistant, and the hash function is the thing that's going to be really difficult to change. So we made sure to choose the quantum resistant thing for the important part, which is the hash function. For the public-private key part, to my knowledge, our public-private key algorithm is ED25519. It is also a very modern, state-of-the-art public-private key algorithm. I do not know if we have as solid of an understanding of its quantum resistance, but this algorithm can be changed in the future. When we find something that is starting to make ED25519 questionable with respect to quantum computing advancements, we can add support for a new algorithm, and we'll probably want to wait to see which ones are handling quantum computers better. And we'll want to probably pick one in the future. And then what you'll be able to do is you can transfer your money from the old account with the like starting to become less secure algorithm to your new account that is secured by the more secure algorithm. And so this choice was not as important to really nail down at the beginning. The hash function choice was much more important, and we chose something that was state of the art with respect to quantum resistance.
Very cool. Very cool. And that was the last question we had for today. I feel like we had so much to learn, and this is an exciting way of bridging into, I think, Web3 with VForge the next 2 days, because I feel like Web3 is so scary for many people to get into. So I love that we started off with like breaking it down.
Yeah, I think part of what I wanted to say with this talk is we have people created these new terms, Web3, dApps, smart contracts, and it kind of, I understand the motivation. We want those terms to kind of describe how significant of a change we think these technologies can be for the world. This is the first time we've been able to do decentralized currencies. That's a pretty huge thing. But at the same time, I think that these new terms also kind of like create barriers. They kind of make people's mental model be like, oh no, this is some new scary thing that I don't understand. And I want to kind of dispel that. You're building the same web applications that you're building with Web 2. You just get to make some new API calls to some new things and potentially work with some new technologies for doing private key, public key signing. And I think you shouldn't be all that scared about it.
Very cool. And thank you, Doug. And y'all heard it from Doug. Like, it's a learning curve, yet definitely worthwhile. And we'll get there. We'll get there with some new API calls and learning it from there. So awesome, Doug. Thank you for joining us today.
Thanks for having me. Really enjoyed it.